Hello, everyone. This is Carl Freund of Cambrian-AI Research. And once again, I'm very honored to have a special guest to talk with you about something I think is very important. Co-founder and co-CEO Aart Geus of Synopsys. So welcome, Aart.
Thanks, Carl. Always a pleasure to talk to you.
Pleasure's all mine. Pleasure's all mine. You've got such great ideas and new innovations. And I understand yesterday during your keynote at ISSCC, you discussed something you call silicon remastering and talked about how this could help companies move technology forward to available process node capacity. So why don't we just open it up and have you explain to the audience, what do you mean by silicon remastering? Why is it so important?
Okay, well, everybody is aware that chips are important, and why are they important? Because when you don't have them, they're really important, right? And so the shortage of chips has been, front and center in many discussions. And it begs, of course, the question, what's the problem? Well, the problem is that chips that were built on older silicon technologies are either running out of availability or can no longer be built on those old technologies because they no longer exist. Now, I want to be clear. I don't want to set expectations too high. This is not a problem you just solve with some techno magic here, but it is a problem that will be recurring. And here's why it will be reoccurring, is that there's more and more of the vertical market segments are looking at adding a lot of silicon technology to their products. And the most obvious case is automotive. And automotive has another characteristic, which is cars last for a long time. You may replace your phone in 2 years or 3 years. A car has 15 to 20 years to go. And so I think that one of the things that will be increasingly necessary is to design chips in such a fashion that they can be remapped at some later date to a newer technology without having to start everything from scratch. So here comes the first caveat. Right now I'm talking about digital part of circuits. The analog mixed signal is more difficult and will over time also need to be handled. But talking about the digital, one of the things that, as you well know, we've worked on now for a while, and the Hot Chips keynote was really showing the first vast potential of what we were doing, which was don't just have a design flow with all the tools, use machine learning, artificial intelligence to look at an entire design flow. And at that point in time, we showed many examples of very sophisticated blocks and advanced technologies that could be designed automatically better than what the traditional manual process with advanced tools would be able to accomplish. And typically we're talking about 3 months going to 3 weeks, that type of ratio of improvement. Now, since then, we have actually pursued this massively, and today about, I think, 5 of the top 10 semiconductor companies are using this in production. So this is being adopted very rapidly, but there's also many more experiments. So how do we tie this to this supply issue? Well, one of the experiments that we started to do is say, well, could we take a design that was done in one silicon technology and migrate it automatically to another and get as good results? So we did that experiment, and the experiment was have the regular design flow do it, then have the DSO.ai, so design space optimization.ai do it, and on the original node we got better results, but that was actually not the point. That was not the point. The point was now take that same design and go to the new node and do the same experiment with one exception, which is we're going to do a third experiment, which is take the learnings from the first node, but apply it to the second node. And it was interesting because we got, in no time, better results using the learnings from the previous node. Now, here was the first caveat, which is, well, those nodes were not that different. Actually, they went from one foundry to another in the similar sort of design space. But, the experiment was extremely successful. And here's the thing that happened literally just, about a week and a half before the keynote for ISSCC, which is they had done the experiment moving to a very different node from a N40 to an N10. And that's, that is 3 nodes difference. And the results were actually excellent. We were able to learn from that original node to the new one. And so we refer to this as remastering, in contrast to another experiment that is just as important called retargeting. And with retargeting, let's say you have a design that's very successful in the market, customer is happy. Now there's another customer said, well, I could buy one of those too if you just change 2 or 3 things. Maybe different I/O, maybe some different storage, whatever it is. And that is a great example of taking a design that you put a lot of work in, and with some incremental changes, you retarget it in the same technology or now also in a different technology. And to me, that is super interesting because now you're dealing in a 2-dimensional space, right? Different nodes, slightly different designs, and all the variations thereof, but with the benefit of learning from the original and having done that automatically. And so that's why this is encouraging. It's not sort of like, oh, tomorrow all deficit of parts goes away, not at all. But I think it is in the line of thinking that addresses these type of problems in a constructive way, and where step by step we'll learn more. But I'm really taking a further step, which is to say, hey, from that learning, we need to see how to design things so that a number of years later, they can actually be ported and or remastered in this case. That's what this is about.
Interesting.
It's fun stuff.
So help me with fascinating. It sounds totally logical and intuitive, but there's obviously flies in the ointment here. First question is, how does that create new capacity, right? Because my understanding is all the advanced process nodes are pretty much consumed by companies like NVIDIA and Intel and Qualcomm and others, and Apple. Don't want to forget them. So where's this capacity come from?
Well, so the first thing to realize is there's a lot of capacity being laid in right now as we speak. And yes, it takes some time to get there. And a lot of that is actually also supported by governments all wanting to have capacity at home, so to speak, right? And that new capacity, nobody's putting in old node in place. So it's all new nodes. And so the assumption is, yes, there will be more capacity there. And one of the interesting notions is that if you can move something from an old node to a new node, if you still have capacity for the old node, now something else can move up the food chain to that node, right? And so if you can move some stuff out of 40 into 10, for argument's sake, that means there's at least capacity being freed up in 40. But it's a complex thing to describe an entire industry with all the nodes, all the things, and in all of these stories of shortages, people often forget to mention that for a year, all the people that now have the storage didn't order anything. Oh, COVID, yeah, we didn't order anything, and now now we're sort of like short. Really, surprise, surprise. But at the same time, we all understand, right? There have been many changes in the world. There have been also deglobalization issues, etc. And on the positive side, I think there's a tremendous positive draft forward with the opportunity space that silicon offers in this intersection of big data and machine learning that I like to call smart everything.
Yeah, I ordered a new vehicle, a European vehicle last year, and the dealer said, well, we're still on target for a November 5th delivery, as long as we can get tire pressure monitoring chips. I don't know how much a TPMS chip costs, but my guess is it's less than $1. So here you've got a fairly expensive vehicle whose revenue is dependent on this small, and I'm sure older technology silicon that they're just running out of. They can't make enough. And also, I would think that this remastering concept not only helps you move from node to node, manufacturer to manufacturer, but also enables you in that process to very cost effectively improve PPA of that new target chip, which can drive more demand and better economics.
Yeah. Actually, the example of this N40 going to N10,
Mhm.
the designer, I vaguely remember the number was like 1.1 megahertz in the N40, and I think it was like 2.6 megahertz in the other one. But that's not an achievement. That is just using 4 nodes further along
Yeah.
technology, right? The fun part was that the DSO was able to get 2.7 or 2.8 or something like that.
Ah,
The exact numbers are in the conference. I forget what they
yeah.
are.
Yeah.
But the point was more that if you can automate the process of getting there, the amount of work is substantially less. And if you can learn from some of the stuff in the a node that's that far away, that means you either learn something about the design, or something about the tools, or something even similarities in the technology. And there are many variables in this, but we're getting our hands around a lot of those.
Hmm. Hmm. Well, I can imagine that companies that would tackle a retargeting don't, because they don't have spare resources sitting around to work on an older design. They're all working on the next generation design. This, because it's so much less labor intensive, you can do the job more quickly and easily, right?
Yeah, and the challenge is for older designs, the economics are often not there. Just imagine, well, the car manufacturer is short the 47-cent doorknob controller, right? And they'll be on their knees to get those, because that $47,000 thing is waiting on the 47-cent doorknob knob controller. But without it, you still don't ship the car. And it's hard to see anybody saying, yeah, I'll put a line in work for you to get you another 10,000 parts. Right? The economics don't get you there. And it's a little bit because of that reason that I concluded we need to have essentially a replacement for just in time. In manufacturing, in the entire food chain of cars, they have for decades tuned this for everybody delivering just what they need just in time, right? But it also was, tuning the cost equation for that pyramid in such a fashion that nobody wanted to ever have inventory.
Hmm.
Well, that works until suddenly you don't have any, and they want some, right? And they need some, and you cannot rekindle such a pyramid in zero time. And so, with an increase of the number of chips and the importance of chips in cars, I think is already an increase right now of awareness in automotive about, so how are they going to manage that? There's a lot of CEOs in automotive companies that talk about car chips. Before that it was like, yeah, that's sort of somewhere deep down in some department, right?
Exactly. Now, if you can't ship the car because they can't get the chip, you're toast. And also, 3 years later, if somebody has something that needs to be repaired and they can't get the chip in the car, now what are you going to do with it, right? You can't
Yeah, yeah,
can't get the chips to repair the vehicle.
yeah.
Yeah, well, our lives are inextricably intertwined with silicon, and I think people are just waking up to how dependent we are on on the semiconductor industry and the supply chain and the manufacturing process. And so having
Well, I think,
government
yeah,
step
they
up
have
to help
woken
solve
up,
that.
right? They have woken
Yeah.
up. And actually, when you said, the guy providing or your car says, well, we're still on target. Whenever I hear that inside of Synopsys on a project, one of mine say, we're still on target. All flags are up. If you're still on target, why do you have to tell me that? That
Yeah.
means you're
That
probably
means there's
veering
probably
off,
a risk
right?
there you don't want to tell me about. Exactly,
Yeah.
Art. Well, I've definitely enjoyed the conversation yesterday at ISSC, and I'm sure a lot of other people are very intrigued by this. So thank you for coming on
You're
with
most
Cambrian
welcome.
AI visions to help people understand what this is all about and how that can impact their jobs and make things better for all. So
Okay.
my congratulations to you and your team. You guys keep driving AI forward. It's having tremendous results within a lot of companies. So congratulations to all of you.
Thank you so much, Carl.
Great to talk with you, Art. Take care. Stay well. Bye-bye.
You too.